All right, well, welcome everybody. Once again, it's 2 hours UTC and it's time for Astronomy Daily Live. So, welcome everybody. You can call me Cosmic. I'm a research astronomer and having way too much fun doing science, astronomy, just completely nerding out on all kinds of things. So welcome. Come on in. I noticed that Bobby just popped onto the panel. Hey there, Bobby. What's happening?
Contraya! Yes, just got done with the mighty KBC. Oh, let me turn this down.
Turn that down.
There we go. Now that's a lot better.
What is KBC? I don't know if I know that.
It's a shortwave radio station that comes on like every Saturday local time or every Sunday UTC.
Cool. Nice. Well, anyway, so welcome everybody. I usually like to ramble here a little bit right at the beginning just to let everybody come on in. I'm going to look at the chat here really quick, see what's going on over there. Uncle Bill saying now. Tom's over in the chat. Hey there, Tom. Nice to see you over there. So excellent. Yeah. So this is astronomy. This is science. This is, tangents are allowed, of course. So, but mainly astronomy here. Because astronomy is big and vast and constantly blowing my mind. Ain't technology great, right? I was just watching live the partial solar eclipse that took place over parts of Asia, and actually that just ended a few minutes ago. But from the convenience of my place here in southeastern Arizona, I can watch a solar eclipse, right? Which that alone is very cool. But somebody has to set up a some kind of a telescope or lens system of some sort, put a camera on it, connect it all up. There's a lot of effort that goes into those kinds of things, and they turn it on to the world, and we all can sit back and watch. Usually there's a little bit of a chat, so that is very cool, because you get to sort of meet people from around the world, right? I mean, there were people from India and Chicago and Arizona, California, all over the place, right? And I mean, it isn't, it definitely isn't like being, face to face, right? But you sort of connect with people that way, and that is very cool. And you get to watch a solar eclipses and lunar eclipses. Those happen at least twice a year, right? But they especially solar eclipses, right? Those occur sort of at very specific places. And so to have or to view a solar eclipse from where you are, that's relatively rare. But somewhere on Earth, solar eclipses will happen at least twice a year, sometimes more. It sort of depends on how things line up. With lunar eclipses, that's a little bit better to see from your location. you basically have to be on the right side of the planet in order to see it, right? So the lunar eclipse that is coming up on at least UT time, January 21st. I think midpoint is somewhere around 5 something UTC, 5 hours UTC. That is going to be seen by at least half of the planet, right? And it just so happens to be sort of the western part. So, I think everybody in North and South America will see it. I think it stretches into, somewhat towards the Atlantic and Europe, well into the Pacific too. I don't think that it hits Asia though. So, the moon is just going to be, blocked by the Earth, right? It's on the other side. But it's very, very cool, to be able to see these things now wherever we are, right? And it definitely for sure is not the same as actually being there and getting, those photons into your own eyes, right? That is a unique, awesome experience. So if you ever get a chance, to do that, do so. Get outside, look up, take a look. Because seeing things is just, it's sort of a subtle way of touching, right? Because what's happening is that the electromagnetic field is wiggling around, right? And that field is wiggling things in your eye, right? Going really, really, really fast, right? And we can sense that, and we call that, wiggling thing seeing, right? So it is a form of very, very, very subtle touch. And so, that's why I say, get outside, look up, take a look at these things, because that is definitely a great way, to connect with nature and the rest of the universe. And that's what a lot of sort of the science of astronomy, science in general, is sort of about, is getting to know nature, and getting to know how it works, but even beyond that, just the experience itself is very, very, very cool. So, all right, well, cool. Well, I hope everybody's doing well out there. And yeah, let's see. So just to follow up on last night's observations, like you saw, I was the previous night, right? It was sort of cloudy at sunset. And so it's like, okay, I'm not going to set up, I'm not going to do any observations tonight, because it's probably going to be humid and all that. And of course, as soon as I decided that, it cleared up, and I don't actually know what the humidity was, but it was probably relatively low, right? Because I got up yesterday morning and looked outside, and there was no fog. There was barely any frost anywhere at all. So it's like, wow, it's dried up, right? Which is what happens where I am down here in the southwestern desert, right, of the United States. Things dry up relatively fast. We get some dry air moving in, and it's like, well, cool. So I looked at the forecast, and it was going to be clear last night. So I'm like, and it's new moon, right? So there's no moon out. It's clear and it's dry, and it's like, okay, perfect, right? So set up the telescope. Can you see the telescope here in the, there it is, right there. So, you know, drag the telescope outside. I'm purposely in a very, very, very dark site, right? So I just have to go outside here. I don't have to drive anywhere. I mean, I'm absolutely blessed, right? But I mean, I did that on purpose, right? Because I want to be on a dark site. So drag the telescope outside, you know, drag the computer outside, took my calibration data at sunset, you know, the t-shirt flats, which are actually, and I mean, I knew this sort of experientially, but I didn't know actually how well regarded t-shirt and sunset flats actually are. Those are actually some of the best flats that you can get. You know, took my calibration data and was watching the temperature drop, and of course, as the temperature drops, the relative humidity goes up, right? So you know, as it got darker and darker and darker, it got cooler and cooler, and the humidity kept going up and up and up and up and up, right? So I'm like, but you know, I was confident, right? It's like, okay, you know, it's going to get to around 50%, and that's just fine, you know, no problem. So it got to 50%, and then it got to 60%, and then it got to 70%, and then it got to 80%, and then it got to 90%. And by the time I was ready to observe it, I think it was about 88% or so. And I'm like, well, okay, you know, okay, this is, you know, usually around 90% things start to dew up, and you know, it's no good, right? So, but you know, I'm looking at the corrector plate, you know, the front of the telescope, and it's like, okay, you know, it's still clear and everything. And so start the live stream and take a look at the corrector plate, and it's just completely fogged over, right? And I look at my little temperature thing here, and the humidity was around, you know, like 90% or 92% or so, right? And it's starting to fog up. So I'm like, okay, this really sucks. But you know, maybe you know, the humidity will sort of peak and then drop again, right? So I decided, you know, to hang out there for a little while and see what would happen. Well, okay. When the humidity got to 98%, I'm like, okay, we're done. And the real bummer was the seeing last night, right? The twinkling of the stars. The stars were barely twinkling at all, which means that the seeing, you know, the conditions, the atmospheric conditions were very stable. It's almost as good as being out in space, right? You know, as if, you know, there's almost no atmosphere at all, right? Now, you know, yes, you know, there was some twinkling, some scintillation, as they call it, but it was extremely small. It's probably the smallest amount of twinkling that I've seen almost ever, right? Now, on top of mountaintops and stuff, it can get really good, right? But from here, it was absolutely stupendous. You know, the Milky Way, you know, was right overhead, and it was absolutely awesome. And there was nothing I could do about it because I was getting frost. I was getting a layer of frost on the corrector plate, and you know, the keyboard was all, you know, sparkly from the frost, and the computer and, you know, the camera, you know, was just getting wetter and wetter and wetter. And it's like, you know, that is no good. That is absolutely no good for the electronics at all. So, you know, I look up and it's like, wow, that's too bad. That's really, really too bad. I looked at a couple of things anyway, but you know, testing other things, you know, testing telescope pointing, telescope tracking, all that. I turned it into, you know, sort of a engineering night, as they call it. You know, just sort of seeing, you know, how things are working and all that. But wow, yeah, that was really a bummer. So now I've got clouds here, and I don't really care that much if the moon is out, but you know, it just makes the sky really, really dark, you know, when the moon isn't out. So yeah, that's you know, that's how it goes. That is the life of a research astronomer. So yeah, here I'll do my weather on the chat too, just like Bobby just did. 606. That, let's see what it says. It says it is right now. It's probably super, super dry again, right? Yeah, 55%. It's like, you know, yeah, that's just not nice at all, right? I mean, it's 50. I mean, last night it was when I quit at about what, 8:30 p.m. 9 p.m. local time. It was 26 degrees. I mean, you know, it was cold, and it was wet, and it was clear as very, very, very clear. And there's absolutely nothing I could do about it. So there you go, Uncle Bill. It says that your location is clear. So maybe you can confirm that or not. You know, it sort of depends. I'm not exactly sure where Nightbot gets its information. So it seems relatively accurate. So but maybe you can confirm that. So does, Bobby, I'm going to ask you this. Does the Nightbot report, is that pretty accurate to where you are?
Well, it does. It's hard to compare with your weather apps like AccuWeather, the Weather Channel app, or the NOAA weather app like weather.gov.
Yeah, but I mean, you've got clear skies there?
Let's see. I gotta scroll. Yeah, I got clear skies.
Yeah, okay. And it's in the low 50s, it says?
Low 50s, but my humidity is at 85.
Yeah. So yeah, you know, wherever Nightbot is getting its info looks pretty accurate. You know, I sort of look at mine here, and it's like, yeah, that's probably about right. So oh yeah, Uncle Bill has a lot of rain. So yeah, that's how it is. That's how it is. All right, well, cool. All right, well, you know what I thought that I would do tonight, and I don't know if I'm going to have enough time to do this all tonight, but what I thought I would do is give you a little bit of a glimpse into what astronomers do. Lots of people think, you know, that astronomers look through telescopes all the time. and that is wrong and wrong. Hardly any professional astronomers, at least, actually look through telescopes. They have some kind of a camera, or some kind of spectrometer, photometer, some kind of a device that's attached to the camera. And if the astronomer goes to the observatory at all, which is actually becoming more and more rare, they'll sit in a nice warm, comfortable room. In fact, the control rooms of telescope domes, the chairs are probably some of the most comfortable chairs that you will ever sit in. They are absolutely great. And I think those chairs are sort of reserved, for the astronomers, because I haven't, been able to find those anywhere else except on top of very, very high mountains. so
How many observatories that you got? I can only know one in Schreiber, Louisiana.
I'm surrounded by major observatories. I've got the Mount Graham site to the north of me that has the Large Binocular Telescope, which is two 8.4 meter mirrors, right? Two big, huge mirrors. Actually, that one right there is one of them, right there. So from this side to this side is 8.4 meters, and you can sort of see little people behind it here. And actually, I'm right there, but of course you can't see me. Yeah. So actually, this is one of the mirrors that's now there. There's also a 6-foot diameter mirror that is run by the Vatican, and there's also I think it's a 10 meter submillimeter telescope, right? So they look in submillimeter wavelengths, which is right in between the radio and the infrared, right in between there. Hello, Space TV. Nice to see you. Great. So that's one, right? I've got Catalina, which is I don't know how many scopes they have up there. At least half a dozen or so. There's Mount Hopkins that has the MMT, which used to stand for multiple mirror telescope.
And before the interruption, I just want to say thanks, Space TV. That's very, very good and stuff, and they light too.
I know. I'm incredibly jealous of that. Incredibly jealous. I'm just gnashing my teeth.
Okay.
What was the multiple mirror telescope that actually used 6 1.8 meter mirrors in sort of a hexagon shape? Quite a while ago now, they actually replaced that with a single 6.5 meter telescope. So I'm actually, they kept the name MMT, but I don't know if anybody's really decided on what that means. So maybe they have. I'm not exactly sure. And of course, I've also got Kit Peak, which is they've got, I don't know how many telescopes there. Wow, at least a dozen. And I think that includes a couple of radio telescopes too. At least, well, they have a radio telescope. They have a submillimeter telescope there too. So yeah. These observatories are generally not accessible to the public, unless they're tours and that kind of stuff. And most observatories do have some kind of public thing, which is great, right? It's really, really great, because people get to see these awesome toys that we get to work with. And I've been so blessed to be able to work with a lot of these telescopes. And so see, I think that is at least one of the reasons why I'm not really hooked on big toys or anything, because I've worked with some of the biggest toys that there are, and so anything less than that is like meh, whatever. Yeah. And there's there are a lot of hidden observatories all over the world that you really don't know about, because they don't want to be bothered, right? They're trying to get work done, and they just want to do their thing, and not have to be bothered, with crowds and everything else
I
like
know,
that.
like the one in Schreiber, when there is a astronomy event going on, they usually open it up.
Yeah, and I think that's great, right? I mean, um, that's what they should do. As long as the personnel are there, to be able to do it, then it's absolutely great. Yeah. Screen going dark. All right. Well, as I said, what I thought I would do tonight, or at least start tonight, is give you just a little bit of a glimpse into what the professional astronomers do. Like I said, they do not look through telescopes, not anymore. And in fact, most astronomers, who call themselves professional astronomers, don't know anything about the night sky at all. They don't know where any of the stars are. They don't know anything, right? And that's how it's always been, and that's how it will be. But that's the cool thing about the science of astronomy, is that uh, um, doing astronomy, you can get into it any way you want. You don't have to know the sky, right? You don't have to. I mean, personally, I think you should, but I mean, if you don't, you don't. You're doing many other things. There are theoreticians, right, who work on modeling all day long, and that helps the observational astronomers make their observations, because the theoreticians will say, well, okay, according to my model, which is like this and this and this and this and this, you should be able to see something, right? And then the observational astronomers go out and they look for it, right? This is how they are looking for Planet 9, right? The observational astronomers are making measurements of the orbits of the bodies in the solar system, the planets and the asteroids and the comets, and that information gets fed into the theoretical models, right? And then the theoreticians, run their models, they run their simulations, and say, okay, if this data is good data, and if my model is correct, then if you look right there at a certain time, then you should find Planet 9, right? And so the observational astronomers, that's what they're doing now, right? You know, they're going out and they are looking. When they, this is how Neptune was actually found, right? This is yeah, Neptune was actually discovered that way, and they, you know, there's a little bit of luck involved with that too, right? Not going to deny it at all, but you know, the theoretical guys said there should be a planet right there, and the observers went there and looked, and lo and behold, there was, right? And we got a whole new planet.
Okay, so Space TB, so what's the main difference between theoretical astronomers and cosmologists?
Cosmology is sort of a specialty, right? Cosmologists are looking at how the universe evolves, and cosmology is very, very much theoretical, but it's also based on lots of observations, right? You know, the expanding universe, so-called, is based on observations of redshift, which we think is caused by a Doppler shift caused by motion, you know, things moving away from us, which sort of implies expansion. So most, I think if you ask most cosmologists, whether they're, you know, theoreticians or the observers, I think they would probably call themselves theoreticians, because they do a lot of modeling, a lot of computer stuff. And that's my point, is that most astronomers, professional astronomers, spend well, they do two things, right? At least half of their time is writing grant proposals, right? Trying to get money, right? Now, it's usually more than half of their time is doing that, 60 or 70%. So, you know, back when I was a student, I saw this, right? I saw, you know, my bosses, you know, who were professional astronomers, spending most of their time not doing astronomy. And I looked at that and said, screw that. I'm not going to do that. That's no way. You know, I mean, you know, what I want to do is astronomy, right? I want to get my hands dirty. I want to get into that data. And so, you know, my path, being a professional, you know, was slightly different, right? Still got to pay the bills, still got to eat, you know, all that. But at least, you know, 60 or 70% of my time isn't spent doing that, right? The other amount of time, most of their other time is spent, you know, working on a computer, either working with data or working with models, right? And a lot of that is actually writing software, right? Writing code to, you know, process the data, or, you know, put the data, you know, to models or write the models, you know, all of that. So that's sort of the direction that I wanted to do in this live stream today. And as I said, you know, I'm looking at the time now, it's already 2:34 UTC. So probably stretch this into tomorrow as well, because you know, this being a daily live stream, I don't feel as though I have to hurry through things at all. You know, if this was happening every week or every month, you know, you know, I'd be like, okay, you know, I'm going to do all of this in one shot, and I'm going to have to hurry a little bit, you know, because it's a lot of information. But with a daily live stream, we can sit back, we can, you know, completely enjoy ourselves. So cheers.
Cheers.
We don't have to hurry. You know, this is a casual, fun live stream, right? Not trying to communicate anything. I'm not trying to teach anything. I'm just showing you some cool stuff that I think is really, really cool. And one of the things that is very, very cool is you know, taking data and trying to understand what you're seeing. You know, looking at data and saying, "Huh, what is going on there?" Right? And this is one of the things that I noticed with actually some data that I've got from my own work that I have a question about. And instead of, you know, sort of doing it myself, I sort of thought, well, you know, let's try to do it on the live stream here and see how it goes, right? See how it goes. So what this is going to involve is some real data and a relatively simple model, right? We're going to put this data into this model, and the model is going to tell us something about the data. And I have a pretty specific question that the model will actually be able to tell me. So yeah, let's get into this a little bit here. So I think I've got this all set up. You know, the one thing that I didn't do, shoot, dang it. Let's see, can I do this? Can I do this really quickly? Yeah, oh, there's one, let me go over to the Discord server really quick and see if I posted a picture, because I want to see. I don't think so. I don't think I did. I'm doing a search over on my Discord server right now. Let's see if we've got it here or not. Okay, well, I do. Haha. All right. Yeah, let's go over here. All right, so I'm going to jump to that, and then I'm going to share my screen here. Let me pop this up here. And then I'm going to share my screen. Come on. Okay, share the screen. There we go. Go to infinity and beyond. And we'll go over here. Okay, so this is an image from my telescope system of a region of the sky around an object called NGC 7243. It's a very loose open cluster of stars. Now, what you're seeing here is not the entire cluster, right? It's just some of the stars that are part of the cluster, right? And what I did, one of the things I'm doing at least, is I am measuring the brightness of some of these stars. And here I'm gonna zoom in a little bit here just so you can really see it. So I'm measuring the brightnesses of these stars, right? Not all of them, but most of them. And there are actually not exactly sure if these are the three that I'm going to be showing, but I'll just use this as an example. In particular, there are three stars, this one, and this one, and this one, right? And what I did is I looked at the brightness of these stars versus time, right? So I took I took about 200 total pictures of this field, 200 2-second exposures, right? So this is a 2-second exposure, right? Showing all the stars in here, right? And sort of concentrating on these three, right? So 1, 2, and 3. And measured the brightnesses of these things, and then I made a plot, just brightness versus time, right? So each 200-second exposure, just measured the brightness of these things and made a simple little plot. Now, for reasons I'm not going to get into, there weren't actually 200 final images. There was something like 131, I think, that were valid, because of tracking errors and bump the telescope, whatever. Some of the data just wasn't any good, right? So I sort of picked out the best ones, and it turned out that there are 131 of these, right? So what I've done over here is I have just some text files here that have my three stars in it, and I've called them target 0, target 1, and target 2. And because I'm a Unix guy, I start with 0 when I count. So Tom can probably appreciate that. So this is what these text files look like, right? And it's just a text file in a whole bunch of columns. Now, most of this is relatively useless, not really pertinent to the example here. The most important column here, though, is this last one, right? So this is the brightness, right? So what I've done is I've looked at this star, and I've simply drawn a circle. Let's use this one instead. I've drawn a circle around this star, and I've just added up the pixel values. That's all I've done, right? Just added them all up. And what I get is a number, right? 48,248.2383. These probably these last two decimal points really don't count all that much, but yeah, I'm bringing it out to 4, just for fun. So this is the brightness. Well, let me rewind my music here really quick. Here we go. So this is the brightness of star 0, which let's just say is this one, right? For image 1, right? This is the brightness of the same star in image 2. This is the brightness of the same star in image 3 and 4 and 5 and right? And it goes all the way down to the end here. And actually, this furthest left column is sort of a image number. All right, so it goes all the way up to 130 because, oh, yeah, it actually goes up to 199. But as you can see, some of them are missing, right? 191 isn't there, 188, 189 isn't there. There's a whole bunch in here, right? Like I said, I sort of picked out, you know, the good ones. So there actually are just 131 lines here, all right? So I did that for these 3 stars, right? So there's target 0, here's target 1, and as you can see, the numbers are different, right? They're lower, so that's probably this star here, right? Because he's fainter, right? Fainter star means lower numbers, less photons. And here's target 2, which is actually even lower. So yeah, those 3 stars probably weren't exactly the ones that I used, but I'm just using that picture as an example because I don't have the actual one here, right? But these are different too, right? So here's even a fainter one, right? So we've got a bright one around what, 48,000 counts. We have a fainter one around like 25,000 counts, and we have an even fainter one around 8,000 or 9,000 counts. So in GNU plot,
faint, fainter, and faintest.
Yeah. And I think actually the brightest one there, I think is around magnitude 8.5 or so. Could be wrong about that, but I think that's about right. So yeah, I mean, it's relatively faint. You can't see it with your own eye, right? You have to have a telescope to see them. So with GNU plot, of course, I can actually look at those values in a graphical form. So let's go ahead and do that. And here I'm going to do this, target 0, 0. So I want to plot column 1, 2, 3, 4, 5, 6, 7. All right, I want to plot column 7. So we'll do that. Target 0, 0, 0 using column 7. Point type is 7, which is just a dot, a black dot. Point size, we can just make it 1 and make them black. And here we go. Bam. So there they are. So what I noticed right away is that at the beginning, they were sort of, if you kind of take the average here, right? Maybe around 45,000 or so. And here I'll make this a little bit bigger so you can see it. All right, so, average maybe around 45,000. But at the end, they were a lot higher. See how they're like slowly getting brighter here? And if you look at the other ones, they're sort of doing the same kind of thing, right? It's like, they're going from fainter to brighter. It's like, what is going on there, right? Well, it turns out that actually has a very, very simple explanation. The moon was rising. And as the moon rises, the sky, right, the background sky gets brighter and brighter. And, since I'm drawing, sort of a circle around this, that actually does extend, well into the sky, I'm also measuring at the brightness of the sky a little bit, right? So to see that kind of a trend upward is actually correct, right? No problem there at all. And since what I'm doing is what's called differential photometry, where I'm just looking at the differences between the brightnesses of these guys, right? I don't really care what the actual brightness is. What I'm measuring is just the difference in brightness, right? Well, these stars are so close in the sky that, you know, the sky around this star and the sky around that star is pretty much should be, right, about the same, right? So I don't really care that this trend is there. I don't really care. But what I do care about is this trend the same in this star as it is in this star, right? One of the other ones, right? Is this the same trend? Well, how am I going to find that out, right? I mean, this is pretty messy data, right? I mean, so the question is, what's involved in trying to understand this trend, right? I mean, it's obviously getting brighter, right? But how fast is it getting brighter? Well, best way to do that is to go to a model and say, let me try to fit a straight line to this data, right? Now, we can do that by eye, right? Really, really, really well. Our brains are really, really, really good at, sort of looking at all this data and being able to sort of draw a line, right? I mean, I can do it right now, right? It looks like maybe like this, right? Drawing a straight line through this, right? And that line is definitely going up, right? It's going from, way down here and up and up and up and up and up to, maybe here. But, that's not very exact, right? I mean, I need some numbers, right? So what we can do is actually go to a model and a technique to actually fit a line to this data. And that is where we get into some math. So here we go. So this is out of a great book called Numerical Recipes. It's an incredible book, and this book, shouldn't be available for free because it's so amazing, but it is. So this is what I want to do starting today and maybe going, towards tomorrow, maybe the next day. We'll sort of take our time a little bit with this and see how it goes. Now, those of you who who haven't done the algebra thing, stick with me, because algebra really isn't as complicated as you might think. I actually think that algebra should be first taught to people very young. 5 or 6 year olds could very easily figure this out. But what it requires, right, is being able to think abstractly, right? Instead of having concrete numbers where you learn, how to add numbers and how, to multiply, and you learn your multiplication.
Please excuse my dear Aunt Sally.
What's that?
Please excuse my dear Aunt Sally.
Please excuse what?
My dear Aunt Sally.
I don't know what that is, Bobby.
It's something that my algebra teacher said it's supposed to be meant for parentheses, exponents, multiplication, division, addition, subtraction.
Oh, okay. Yeah, I think a lot of people get I'm sort of hung up on all the rules and all the procedures, and that's what makes things complicated. When things really aren't that complicated, um, and that's sort of why I'm going to go through this, because it really isn't. What we're going to be doing here is some algebra, actually some calculus, and you'll see that it really isn't as hard and as complicated as they sort of say it is. When you're learning all this stuff. Now, I only learned how actually easy all this is after the fact, right? Once I was done with math, right? I mean, I went all the way with math. I've done all of it.
I just
And
got
it's
like all the
only,
way up through algebra. I didn't do any calculus and stuff.
yeah, cool. You'll have no problem with this though. Really. It's just not as hard as, they say it is. So yeah, let's dive into this. So what we want to do, right, is we want to take this data, right, and we want to fit a straight line to it, right, and it's going to look something like this, right? It's going to sort of go through the data like that, right? So there's a lot of scatter, but we're looking for just a single line, right? And so the equation for a straight line is this, right? It's y sub x, where y or x is just a function of y, which means that x is over on that side, right? And so here's the equation for a line, a plus b times x, right? B times x are multiplied together, and then there's an a out here. B is commonly called the slope of the line, and a is commonly called the y intercept. The reason why it's called the y intercept is if x is 0, then this side is 0, and you just get y sub x equals a, right? So probably what I should do is make a little drawing. Can I do that? I think I can do that over here. Let me actually let me set that up first. So I'm gonna unshare just really quick. Let me get this set up. Yeah, maybe we'll just talk about lines for today, and then we'll actually get into the code and everything tomorrow, because I'm noticing that the time is creeping up on us a little bit. All right, so I have set this up. Now, this is going to be me drawing with a mouse, so it's going to be really crude, but I will do my best. As I said, I'm not trying to teach you anything here. I'm just trying to show you some stuff. So if I were to teach things, I would have a plan. I don't have a plan.
Definitely.
All right, so sharing a screen again. All right, so here's this. So if we draw a y-axis here, and I can actually think I can actually draw a nice straight y-axis. Okay, here's a nice straight y-axis, and that's pretty straight, at least. And let's draw an x-axis, right? Here's an x-axis. Now, these things aren't going to line up exactly, and they probably aren't going to be exactly straight, but you get the idea, right? So now let's draw a line, right? Just sort of an arbitrary line. My mouse is not behaving here. Here we go. And I'm going to sort of go over here a little bit. Let's just draw an arbitrary line. Whoop! Why are we doing that? Oh, I don't know. Not quite sure why it's doing that. Can we scoot you back over? Let's try that again. Maybe it doesn't like me going over here. Okay, there we go. Okay. All right. So, and actually I can do this. So there's, let's make this a blue. So there's x equals 0, right? And I know that's kind of hard to see. Let me zoom in a little bit, maybe. It's still a little bit hard to see. Okay, so when x equals 0, you're exactly on the y-axis, and that's why this is called the y-intercept, right? Because this line is crossing the y line, right? And that's why when x is 0, y sub x is going to equal a, right? So a is, and let's just say that this is y of 0, and let's call this 0 here for x as well, right?
We're waiting for you, Daniel Brownie.
Hey there, Daniel. So a, in this case, is going to be whatever length it is from here to the intercept here, right? So that's just this length, right? Now the b is what's called the slope. It's the slope of this line, right? And the slope of that line is actually very, very easily computed. If you take any point on this line, right, and do that kind of thing. In fact, we can go all the way down to the bottom if we want here, right? And if we take another point on this line and do exactly the same thing, and then we do a little right triangle thing. Whoop, I didn't mean to move that. Let's see if I can do it over here. I'm going to try to line it up slightly. Oh man, it's really going to mess with me now. I'm bending the line. Let's just do this. Oh, it's still going to do it. Dang it. I'm trying to extend this line out over there. Extend this line out over there. Okay, so if we take, if we look at the y value here of this point, right, which is going to be over here, and the y value of this point, which is going to be over here, we're going to get a particular distance here, right? Let's just call this capital Y, right? And if we look at the x point here and the x point here, we're going to get a certain x here, right? And the slope of this is just y divided by x, right? And y divided by x in this case is just this b, right? It's just the slope of that line, right? So let's just take an example, right? If a is 0 and b is a slope of 1, right? Then this goes away, right? Because it's 0, and y sub x is going to equal x, right? So if x is 1, then y is 1. And if x is 2, y is 2, right? If the slope is different, say that it's 2, right? Well, then y is going to be 2 times x. So x is 1. 1 times 2 is 2, right? If x is 2, then y is going to be 4. If x is 3, then y is 6. Hope that makes a little bit of sense, right? So this is just the equation of a line. That's all it is. You know, if you want to get into more of that, you know, you can do that on your own. But this, you know, since we want to fit our data to a line, we have to know what a line actually is. And, you know, mathematically, that is what a line is. That's how you describe a line. Now, you know, we could extend this and say, well, you know, maybe we don't want to fit this to a line. You know, maybe we want to fit it to a curve or some kind of exponential thing, or, you know, whatever, right? Well, you can do that, but, you know, the mathematics are slightly more complicated. Straight lines are relatively easy, as you'll see, right? So, but what we want to do, right, is figure out what the slope of the line is and the intercept, right? So going back to this data, right, I want to know where at, you know, point 0 here on the x-axis, where does that line hit the y-axis, right? Looking by eye, right, it's going to be, yeah, somewhere around here, right? Maybe around, you know, maybe a little bit more than 45,000, right, in this case. But I also need to know what the slope of this line is, right? So how is the y value changing as x changes, right? Because at an x value of 0, y is going to be, like I said, you know, somewhere around, you know, like 45,000. But like at an x value of 80, right, the y value is going to be what, maybe around 50,000, right? And x equals what, 131? It's going to have a y value, I don't know, 52,000. I'm not exactly sure, right? So what we want to do here is we want to figure out a way to fit this data the best way that we can to a line. Now, you know, maybe this data isn't linear, right? I mean, maybe it isn't. I don't know, but we're going to fit it to a line and sort of see what that does. And the question that I have, right, is this slope, right, which is actually representing how the star is brightening over time, right? So is you know, star number 0 here brightening in the same way as, I'm going to go back to star 1, right? So is this slope exactly the same as the other one, or, you know, relatively close? And is the slope of star number 2, is this slope about the same? Now, looking at it on plots and everything like this, it's really, really hard to tell, because, you know, this thing is, you know, this plotting program is rescaling itself, you know, trying to fit all the data into one screen. So we really, really, really don't know. And I would like to know exactly, you know, fitting a straight line to this, what is the slope, right? Now, my guess is is that the slopes are more or less going to be about the same, right? They're not going to be exactly the same because there's a lot of oh, doggy alarm.
Uh-oh.
These slopes aren't going to be exactly the same because there's a lot of scatter with this data. So I don't expect them, to be exact, right? But I also don't expect them to be, like insanely far off, right? They're all going to be more or less, I hope, about the same, right? And there's a method to doing all that, and it's called the method of least squares. And this is the actual equation right here that we're going to get into. And I think I'm going to reserve that for tomorrow, because I don't really want to get a lot towards derivations and all that kind of stuff, and you're starting to see partial differential equations here and all that kind of stuff. So I don't want to get into the math much, because that's not the exciting part. The exciting part is actually writing the code, writing the software to do this, and looking at the results. But what we can get at the end, right? And this is actually one of the cool things about being a programmer, right? It's almost like, you know what? I don't care what the math is. Tell me what I need to do in order to, get the numbers I want. I will write the code to do it, and that'll be that, right? So in the end, what we actually get is these equations for A and B, and that's what we want. We actually just, it's all we want are these last two equations here. It's all we want. And this is what we're going to put into code, because once we know A and B, then we can plug any X in here we want, and we'll get a Y that is a straight line best fit to our data. And that's what we want. So yeah, I think let's reserve that for tomorrow. The writing of the code. The writing of this code is going to be super easy, but it does involve sort of interpreting this, and so we can walk through all of that. But I guarantee it's really easy to understand. But bottom line is that what we want in the end is what the slope and the intercept is, and that's what these last two equations give us. Once we have these, we can actually draw a nice line right through this, and we can compare the slopes and see if the slopes are the same. And I'm hoping, I'm thinking that they're pretty close to being exactly the same, but we have to find out, right? I mean, we have to let the data tell us, and that is kind of the neat thing too, right? Let nature tell you, what's going on, and then you sort of redirect your efforts that way, right? I mean, when we do these computations tomorrow, maybe the next day, I don't know, and the slopes are very different. Like one slope might be a value of 1, and another slope might be a value of 5, right? Well, that's very different, and it wouldn't explain my simple explanation of just the moon rising and the sky getting brighter. There has to be another explanation, and these models can inform us about what's going on, and saying, well, what you're thinking there isn't quite right. So you're going to have to go back and you're going to have to look and see, there's got to be another explanation. But just looking at the data, by eye, it sort of looks like all those slopes are the same. But we really won't know until we're actually able to solve for those final two equations, which I'm going to write the code right on here live. You can see all the C code and everything. I'm going to write this in C. There are lots and lots and lots of ways to do this. So what I'm going to show you is sort of one of my ways of doing it. There's lots and lots and lots of different ways of doing this. I'm just going to show you one example. But yeah, I think that'll be a little bit fun, and I'm sort of anxious to see what that slope is. The intercept, of course, is going to be different, because that sort of depends on the brightness of the star, right? The brightest one is going to be up here, and the faintest one is going to be here. But I'm hoping, guessing at least, that the slopes are pretty much the same. So yeah, we'll stay tuned for that. Cheers, and yeah, I think I'm going to get out of here for now. All right, well, take care, everybody. I will see you in a little less than 23 hours from now. So have a great evening, a great day. Make sure to subscribe if you haven't yet. Most importantly, spread this around. I'm just here, sharing a passion. Like I say many times, I'm not really here, to teach anything or to communicate science or anything. I think that'll actually happen all by itself. What I'm doing is just sharing a passion. I love this stuff, and I can talk about this and work on this and do this all day and all night, and I actually usually do. So but it's nice to talk about it too, and share it. All right, well, cool. I think it's time to get out of here. So take care. And like I said, I will see you in a little less than 23 hours, just a little less than one spin, right? I mean, we're all spinning around on this planet really, really close to about 1,000 miles. Well, yeah, 1,000 miles an hour, right? Right now, where you're sitting, right? You are moving to the east at 1,000 miles an hour. Imagine that. Now, even somebody with short hair, 1,000 miles an hour would just blow my hair back, just blast it, blast it. So why isn't it? Why isn't it? Do you ever think about that? I mean, why don't you feel any of that? I mean, we certainly see it, right? The sky is moving, right? Which probably isn't actually the sky moving, it's the Earth rotating, right? So as the Earth turns this way, things look to be moving that way. So we see evidence for a very, very, very rapid motion. Why don't you feel any of it, right? I don't know. I mean, we're really, really used to it. It's really, really smooth. But my guess is that, it's a lot like moving in a car, right? When you're moving in a car, and sort of protected, right? You don't feel the wind. You don't, you relative to the car, you're not moving, right? Well, the same thing is happening here. We're sort of, moving with the Earth, right? We're sort of attached, and it's really, really smooth, right? Super, super, super smooth, not bumpy whatsoever. So yeah, it's a really, really nice ride. But it just always amazes me to think about how we're moving, And that's just one kind of motion, right? There's lots of different kinds of motion. There's us spinning around on the planet. There's us going around the sun. There's the sun going around the galaxy. There's the galaxy going who knows where, right? And then, if we're in some kind of a universe, right? Is the universe moving too? And then it's like, well, when you start talking about things moving, that's all relative, right? So, yeah, I mean, it gets mind-blowing very, very, very fast. But, it's nice to think about. So, all right, you guys, I'm really going to get out of here now. So take care, and I will see you later. Bye.
Later.